There are a lot of people in the United States right now who think the country is falling apart, and at least in one respect, they're correct. Our roads and bridges are crumbling, our airports are out of date, and the vast majority of our seaports are in danger of becoming obsolete, all the result of decades of neglect. None of this is really in dispute. Business leaders, labor unions, governors, mayors, congressmen, and presidents have complained about a lack of funding for years. But aside from a one-time cash infusion from the stimulus program, nothing much has changed. There's still no consensus on how to solve the problem or where to get the massive amounts of money needed to fix it. Just another example of political paralysis in Washington.
In 2007, the I-35 bridge in Minneapolis collapsed in the height of rush hour. 13 people were killed and 145 were injured. In hindsight, there were signs of this impending doom, but there was no system in place to notify inspectors of the deficiency. We wish to introduce a widely implementable system to measure and/or monitor the health of a bridge in real time to prevent tragedies like the Minneapolis Bridge using state-of-the-art technologies available to analysts and engineers. Structural health monitoring is the task of assessing the structure's integrity in order to determine whether that structure is able to meet its operational requirement. Many infrastructure systems continue to be used despite aging and the associated potential for damage accumulation.
The fact that nearly 70,000 bridges in America, 1 out of every 9, is now considered to be structurally deficient.
These arch bridges actually has a structure built under it to catch falling deck. See that structure underneath it? They actually built that to catch any of the falling concrete so it wouldn't hit traffic underneath it.
That's amazing.
It all comes down to funding. Right now, they can't keep up with it. 300 bridges become structurally deficient each year in the state of Pennsylvania. That's 1% added to the already 23% they already have. They just can't fix them fast enough.
With rising costs and shrinking budgets, the ability to monitor the structural health of these systems is becoming increasingly important from both economic and life safety points of view. For all these reasons, it is necessary to develop methods able to identify damage at its onset and to provide infrastructure's authorities with information on the structure's integrity. Such information is necessary to make educated decisions regarding the system's maintenance, repair, and retrofitting. The structural health monitoring techniques that we introduce try to answer the following questions. Is the system damaged? If so, where is the damage located? What kind of damage occurred? And what is the extent of the damage? Finally, what is the remaining useful life of the infrastructure given the identified damage conditions? In order to answer these questions, we use techniques that are used by civil engineers to design these bridges. Finite element simulation software. Finite element simulation techniques provide an understanding of the response of a structure under loads when the geometric and material properties are known. In a regular design process, one finite element model is generally used to capture the response of the structure. In our approach, we create a database to capture the response of every state we can imagine, damaged or not. For that reason, we use OpenBrim to define our bridge parametrically. We then vary the parameters like crack width, crack location, deck thickness, and many others. This enables us to create a simulated response for every permutation of the defined parameters. The acceleration response of the structure under train loading is recorded for future analysis. By measuring the bridge response with sensors strategically placed on the structure and intelligently analyzing these measured responses, it is possible to identify damage occurrence. OpenBrim is used to parametrically model the bridge. The parameters are used to create mass stiffness and damping matrices. We apply loading scenarios like trains or an earthquake. Larsa 4D is used to run finite element simulations. Results are recorded as sensor locations, and the process is repeated for other parameters. The result of this process is a database that maps every parameter to a response. In the data reduction phase, we first use piecewise linear interpolation to reduce the data. The simulation data is then grouped according to a single changing variable, or parameter. We interpolate the simulation data with the sensor data. Redundant parameters are then removed, thereby cutting the dataset in half. So what do we do with all this data? The end goal is to develop a method to relate real-world bridge data to our generated data. Here you see graphs of two parametric states of a bridge. The plot in red represents a healthy bridge. The second plot, in blue, represents a bridge with a deteriorated or thinner deck. We measure the similarity of these two bridge states using the Euclidean norm of the residuals. Now we can do this for both the time domain as shown, or in the frequency domain. Here we've taken the fast Fourier transform of the same data, again with the healthy state in red and the deteriorated state in blue. At about 2.4 Hz, the bridge response becomes bimodal from a single wide peak. The Euclidean norm will account for this variation. We can then perform our Euclidean norm calculation to compare every bridge state to every other bridge state. The resulting map, shown on the left, illustrates a region around the two states of low similarity, shown by the yellow coloring. If we zoom into this map, we see some other interesting correlations. It appears that every 115 columns, there is some repetition in the figure while getting slightly darker. It turns out that every 115 rows, the deck material density parameter is changed. Another significant feature we notice is the crisscrossing yellow lines throughout the figure. It turns out that one of these lines occurs when the modulus of elasticity of the main girders changes. The other line is when the bearing spring constant changes. The bearing spring is the main point of connection between the bridge columns and the deck itself. This makes sense since the main girders and bearings are such a critical aspect of the bridge structure. There are many necessary improvements needed in order to improve the methods we developed in this project. These include alternative modeling methods for the bridge itself. We also need to validate whatever models we choose against real-world bridge data to determine their validity. In order to develop a machine learning aspect to this project, we need a more advanced distance function. Euclidean distance simply does not capture enough information for a machine learning algorithm to operate. Finally, we should develop a reversed recommender that takes as an input real-world bridge data and outputs the expected parameter set.